Hello, everyone. Welcome to the webinar. We will wait maybe one more minute to allow people to join. Thank you. Hello, everyone. We will wait 30 seconds more and then we will start the webinar. Okay, I think we can. So thank you very much for joining. Welcome to the third webinar of the ACTonNBS webinar series that are hosted by the ACTonNBS project. My name is Juraj Jurik. I'm working as a Director of Nature-Based Solutions program at the GAB Foundation in Basel. And I will be moderating this session with my colleague, Andrew Simons, who you can also see next to me on the screen. For those of you who don't know the project, the ACTonNBS project is a climate kick-funded project, also with a contribution from MAVA Foundation. And its objective is to collaborate and coordinate cities in Europe that are working on climate adaptation strategies using primarily nature-based solutions. So we are supporting our city network with needed knowledge, expertise, technical and financial expertise, and of course, network to allow them to properly address the climate and social vulnerabilities. The topic of the webinar today, of course, is nature-based solutions for water, meaning for water safety, water security. As most of us know, climate change, habitat loss, and human activities such as urbanization are having a detrimental effect on water cycle, on the retention capacity of the environment, and are leading to a lot of hazards, mainly flooding. For example, since 2000, there were more than 100 major floods in Europe, causing more than 700 losses in lives and more than 25 billion in uninsured economic losses. So nature-based solutions, of course, could deliver better ecological quality and availability of water, as well as provision of flood mitigation services for cities. And this webinar will provide you with such examples that you can use in your work and in your network, and hopefully you can get inspired and use this in your sphere of influence. To the structure of the webinar, you will hear 3 presentations. Each presentation will be for, let's say, 10 to 12 minutes. And then you can use chat functions to ask questions. And at the end, we will have a Q&A session where we will try to answer most of your questions that you will ask. The webinar will be recorded, so of course you can use it as a knowledge resource afterwards, and you can get back to it if needed for your reference. I will hand over to my colleague Andrew Simons, who will introduce the first speaker. So thank you very much again for joining, and Andrew, the floor is yours.
Thank you, Jure. So we're pleased to welcome our first speaker, Kimberly Wong, who is Senior Operations Engineer for the City of Burnaby in Canada. And we're especially grateful that she's joining us given the time difference with British Columbia. She will speak on a nature-based solutions project that the City of Burnaby is undertaking with Deltaris along Burn Creek in the context of flood resilience, updating dike standards, and the multi-stakeholder engagement process. Kimberly, please, the floor is yours.
Well, thank you very much for the introduction. And let me just see if I can move along my slides here. Hi, everybody. And let me just confirm that I can move my slides along. Apologies. Okay. Well, thanks for the introductions, and hello from my kitchen on the west coast of Canada. I'm here today to tell you a little bit about our project that we're getting a little bit of help from Deltares on. The project is nature-based flood resilience along Burn Creek. We're still working on the project right now, and this has already been quite a journey because this is our first opportunity as a city to have discussions solely on nature-based solutions. So just for some context, Burnaby is on the west coast of Canada. We are the immediate neighbor to Vancouver along the west coast in BC. The area of Vancouver is just under 100 square kilometers. We have about 250,000 people in population and growing. Burnaby is a park city where we've been successfully managed to preserve about a quarter of our land for green space, which includes 90 creeks and 2 lakes. Even though the terrain in Burnaby is fairly hilly, our land stock is fully built out, and development is still quite active, with a lot of the low-rise towers being converted into high-rise towers, especially in our 4 urban town centers. There's quite a bit of industry in Burnaby with high-tech companies, universities, and especially in the study area of Burn Creek, there's quite a few film and TV studios as well as agricultural land. So this is the catchment area of Burn Creek. It is close to the south end of the city. So Burn Creek runs from the east end to the west into the regional Fraser River. And above the yellow line on the map here, you can see it's the uplands, and it's a hill that rises up north to the ridge where we have 2 town centers, and then south of the yellow line is the flat lowlands where we have golf course, agricultural land, film studios, and industrial land. Burn Creek consists of 3 other subcatchments with smaller creeks that flow into the main stem of the creek in the lowlands. The provincial government oversees and sets requirements on the city's maintenance of dikes in the lowlands. So along both sides of the creek, up to around this yellow line here, we have what is called registered dikes that the provincial government oversees. And this whole catchment was a part of a drainage study that Kerwood Lido has worked on for the city in the past, and Deltares has used the model from the drainage study to model the effects of nature-based solutions as part of this project. So we knew very early on in the project that there would be many stakeholders, and many of them will have different interests. And especially the conflicting interests that begin in the senior government level, where design standards or requirements for dikes do not allow for trees or vegetation near the dikes. And this conflicts with environmental legislation that requires quite a vigorous and lengthy permitting process for removal of trees and vegetation next to water courses. And if the city follows local diking standards for raising our dikes or upgrading our dikes, as you can see in the figure on the bottom left, the new dikes require much larger footprints, which conflict with other city departments' initiatives, such as planners in the planning department who wish to preserve our industrial land stock, and then also our parks and our golf services department who wish to preserve land for the park and recreational uses. We knew that there were already many discussions that were required at the government level. So the first workshops that we had were limited to internal stakeholders so that there could be a forum for open and honest discussions. And we would have answers before we approach the public, such as the Burn Creek stream keepers, indigenous groups, and property owners. So when you're dealing with many stakeholders that have different conflicting interests, it was important for us to set the stage by demonstrating that this is a city initiative and that there will have to be compromises and sacrifices in the departmental level and then as a city as a whole. That we made sure that everybody understood that these compromises and sacrifices may be short term, that it could be, for example, impact to access during the construction phase, or it could also be long term, which could be loss of land or operational and maintenance requirements. An example is shown here on the right side where in the 80s, the city had to address some of the flooding issues along the creek and took a pretty bold move in reshaping the channel. And that led to temporary damage to vegetation and habitat. So that was a sacrifice that was made, but with the understanding that it would be, the vegetation would restore, and it was only a temporary means to bring back healthier habitat along the stream. Another example that came up when we were very early on in our discussion was a criticism that came from our golf course. And basically they came into the discussion saying that we cannot lose any land along the golf course in the golf course, and they're not willing to have any impact on their operations. We understood that, but we had to paint the picture that and show them through modeling results that we need the land, and we need some land, and also that their parking lots would actually be close to underwater in the future climate change scenario. So that brought them closer to the table for discussion, and we hope that we will be able to work with them closer in the next stages of the project. So at the beginning of the study, it was important to highlight the key challenges along the creek. We had this list of challenges which we would reflect at the end when we have options. So key challenges along Burn Creek include flooding and stormwater surcharges, erosion along streams that are fairly steep, lowland and upland maintenance requirements, low stream ecological health, increase in impervious areas in the watershed due to development and urbanization of streets as well, point source and non-point source water quality concerns, as well as reduced groundwater-based flow. In the study, we also had help from Deltaire to look at future challenges, and we selected scenarios that would model climate change. So I won't go into this in detail, but basically we selected an increase, a 50% increase in design storms, and also a 1 meter increase in sea level rise as part of the boundary conditions of the Fraser River. So it was important for us to establish an understanding of basic water management strategies when we came up with the options to discuss and to model. So we learned that it is typically in water management is most beneficial when you can store and use water whenever possible, as high up in the catchment as possible. And if you can't do that, then retain it, which would, for example, be in rain gardens or infiltrate the water in the ground. And only it would be the last resort when you have gray solutions to drain the water or block flows from downstream. So we came up with these solutions here, which range from green solutions all the way down to the gray solutions, and discussed these solutions. So the gray solutions are still on the table, but we focused on modeling the top 3 and discussions around the top 3 here. So in terms of emergency flood storage area, we, in the workshops, we picked locations, but we had challenges finding space as well. We understood from the model that it would lead to temporary storage of peak discharge volumes, and it works best for long duration events. The most beneficial option that we saw in the modeling was upstream green catchment measures, which reduce peak inflow. And this has more effect on short duration events, and the results actually impact the entire water levels along the entire creek. We also looked at creek widening, where we need space, and there's very limited space in the lower reaches of Burn Creek. So here's an example of the results from the workshop, where we found areas through collaboration and discussions for water widening of the creek in the lowland areas. And here we can see that even this space that we can find can lead to some effect, and which is approximately 10 millimeters of rainfall on paved areas in the catchments. We used also the circle tool that Dalter's provided to get a better understanding of other green features, and we're able to live plot in different measures in both private property and on street, and the results related to downstream effects, climate and water quality were presented immediately. So this was quite interesting for us, and to learn about the different measures as well, because there was quite a long laundry list of measures that were introduced to us. So this is my last slide. In summary, when we looked at the nature-based solutions versus the traditional solutions and compared it against key challenges in Burn Creek, you can see that the gray solutions, such as elevating dikes and pump stations, only provides one benefit, which is flooding and storm water surcharges, so they only address that. Whereas there's quite a bit of co-benefits with nature-based solutions. And when you look at the upstream green catchment measures, it basically checks all the boxes. So that concludes my presentation, and I'm happy to take any questions.
Thank you, Kimberly. I think we're taking questions at the end after all of the speakers, but that was fantastic. We're now pleased to have Professor Mario Schermer, a hydrogeologist and geophysicist who is group leader for hydrogeology at EWAG, the Swiss Federal Institute of Aquatic Science and Technology. And he's also an associate professor at the University of Neuchâtel. He'll give an overview of the RECORD project, standing for Restored Corridor Dynamics. The RECORD project in Switzerland focused on river restoration as an essential tool to reduce flood risks and impacts, to improve water quality, and for ecological restoration. Mario, please.
Yeah, thank you very much. Welcome to my presentation. I will talk about complex hydrological and ecological interactions along river courses. And here's just a picture to remind us what we also heard from Kimberly. There are lots of flooding in the past in many countries. And because of these floods, we thought we should probably do something to the rivers in order to get rid of those floods. So we engineered rivers to have flood protection, but we also engineered rivers for other reasons, like that we can have shipping all year round or irrigation. In Switzerland, the big point is hydropower production. Having engineered rivers, we still see pictures like that. And this is Dresden, my hometown, in the year 2002. This was the biggest flood ever recorded in Dresden. And although so many measures were taken to prevent things like that. And this was one of the triggering points why we really thought we should go into research to really understand what's going on and how we can help to prevent that. And this is the RECORD project we started just when I arrived in Switzerland 13 years ago. And this is the Thor catchment in Switzerland. And this is the longest river in Switzerland without any retention areas. So no natural and no man-made retention areas. This means a very dynamic river. And this is here a picture of the site I will talk about. I will talk about a bit about this forest here. It's a floodplain forest that was disconnected from the river for more than 100 years and had to be reconnected. So give the river more room. And also I will talk about some drinking water production problems or potential problems. And this is how the site was looking like just when restoration finished. So, but this is a snapshot in time because a river that is restored moves, of course, a lot, and there's always erosion and deposition and so on. Now, this is the river seen from one of our observation towers. And I want to show you how dynamic this river can be. Under these conditions here, the river has about 50 cubic meters per second water. And then there are rain events, as you see. And then overnight, the river is really increasing with the water level. And this is about now 900 cubic meters per second, which means a huge increase just in a few hours. So this dynamic, so in these floodings that came that caused, of course, damages along the river reach, reduced damages in upstream, but even had more devastating events downstream. So in the early 1990s already, was some discussion about river restoration. And the site I'm talking about here is Niederneuenfonn. But of course, there are many challenges, as we have also seen in the previous talk. And some of them are shown here, conflicting interests. And of course, also in Switzerland, we really appreciate our natural environment. So biodiversity is something we really want to preserve or want to regain. But there are also problems with drinking water production, as I will show. So economic considerations, of course, public acceptance and so on. So all these conflicts have to be looked at when you do a restoration project. So the motivation actually to restore the site there in Niederneuenfonn was to achieve a good ecological status. So to get closer to pre-engineered conditions. but also contribute to flood protection. Because these floodplains are threatened ecosystems, and this is true especially in urbanized areas or areas where you have agriculture. So the Swiss plateau has many of those examples. And then there came, in 2010, there came a Swiss law out where these things, to get a good ecological status and to contribute to flood protection, the Swiss government said over the next 80 years, 4,000 kilometers of rivers need to be restored within Switzerland. And they provide 60 million Swiss francs every year. And actually this amount is topped by the local governments, and so it is even much more nowadays. And of course we know these river courses have multiple functions. And one of the functions is that these aquifers that are close to the rivers contribute to 40% of Swiss drinking water. So when you widen the river, this might be a problem that you face. So then in 2002, river restoration started. Here you see how this area looked like. So the big machinery came in, took out engineering structures, and the river became restored. And this is then after restoration, 2004. So a snapshot in time, as I said. Here, this is this floodplain forest that is now reconnected to the river. So there are from time to time, this forest is flooded, so back to more natural conditions. And close by here, there's a drinking water well I will also talk about. So this is then the new river after restoration. So people were happy to get back to the river, so they could access it now better. They could see the gravel bars, can go hiking there, fishing and so on. And also species came back like the beaver and bird population, gone for more than 100 years. But still the river is wild, and here you see some damage that was done, and so we had to go back to do some construction so that this damage doesn't eat too much into the plains and into the forest. And then after this intervention, then the Thur River still, of course, restored. But now it was much more under control. And now slowly, we see now after almost 20 years after the first restoration started, so to getting to somewhat kind of like equilibrium, although it's still changing. So there are still at parts of the rivers erosion, and then other parts we have deposition. So this is a constantly changing environment. And then we came in with this record project, and I really want to show only two examples, but we did lots of field measurements, different groups of scientists worked together. We did targeted experiments, a lot of modeling at different levels. And the goal was to really determine what is the functioning between the river corridor, and the aquifer. And the aquifer are important for drinking water production. And we wanted to get really a mechanistic understanding, what is going on and how can this maybe be influenced after we understood it. Because we said when we don't have a process understanding, we will never be able to do predictions, or when we do predictions, this may remain speculations. Here, a picture of the restoration, before restoration, when you have these levees, so the rivers in between. In Switzerland, we have these losing conditions. So the river loses water into the aquifer, and this can be pumped through a pumping station for drinking water production. And when you have river restoration, the engineering structures are taken out, and now the river is wider. So you have better infiltration, but also the distance between the river and the well is reduced. And in Switzerland, we have the law, the water has to be at least 10 days in the subsurface before you can pump it and supply it as drinking water without treatment. So it's important to get to know how long the water is in the subsurface. And the second thing is, of course, this floodplain forest was reconnected to the river. So this is just to show you some of the monitoring we did. So many different scientific groups, as I said, worked together. This is in one of the observation towers where you saw this movie in the beginning of my presentation. So lots of different measurements. And I want to show you now one example that we as hydrogeologists did. So we wanted to know how quickly water flows from the river to the well. So we could use these dyes here, but people don't like dyes so much because the river is green for a long period of time. And also the hydrology that you investigate is only valid for the conditions that the river has at that point in time. So we developed then a method that uses natural tracers. Natural tracers are electrical conductivity and temperature in the river and then in the subsurface. And here we have the river, and here we have the well. And when the river is changing in height, this passes through and pushes the water quicker into the aquifer. And so these, I want to show you now a little movie. Here you see the head in the river and in the well. Here the electrical conductivity in the river and in the well, and here the temperature, how it is changing. And now we have an event. The river goes up and the water moves through quicker, and electrical conductivity arrives, and the temperature is a little bit retarded, but the signal from the river is passed through into the well. And this time difference we can calculate and know how long the water is in the subsurface. And when we take this now for not only one event, but for an entire year, for instance, we see here an example. So here, this is a well close by the river, and a lot of the water is only moving in average less than a day, and the water arrives. Some water in the year is earlier, some is later. And here's the drinking water well, and we see here, on average, the water is 11 days in the subsurface. So the water during flooding events cannot be used for drinking water production, but a large part of the year you can use this water for drinking water production. So this method we developed, called the deconvolution method, and this can be used now for to measure the travel time in the subsurface. And the last example from this large research project I want to show you, biodiversity, because we wanted to get a better ecological status. So here are the sampling sites for the non-restored, still the engineered part of the river, and we compared this to the floodplain and the floodplain forest. And so don't want to go into details. So our biologists, ecologists, they did lots of different measurements, and they counted all the species and so on. And I just want to show you the results, which were encouraging. So from vegetation up to the little creatures, up to bacteria, in all of them, in the restored part in blue, the total species richness is larger compared to the generalized part. And so this means the restoration really was a success in terms of ecology and biodiversity especially. So with this, I come to the last slide. In terms of replicability of river restoration, because the site was one of the first. We realized, we did also research at other sites, we realized each site is different. And with the drinking water production in Niederneunvon, this is close by, and floodplain forest of national importance. So this drinking water could be protected, and the forest has a much better biodiversity. We had a multidisciplinary approach to understand these systems, this is clear. And then the knowledge we gained was also then used at other sites that were restored afterwards, and also in other Swiss rivers. And also the Swiss law that came out to restore these many kilometers of river courses in Switzerland helped, of course, the restoration projects. With this, I'm at the end, and in the after the last presentation, I can also answer some questions you might have. Thank you very much.
Thank you, Mario. Quite powerful to walk through an NBS project over such a long time horizon and from so many different angles. So our final speaker, Professor Michael Lupus, an engineer and associate professor for sustainable development systems at the University of Athens, will present the co-design, development, and evaluation of nature-based solutions applied to the Spercheios River Basin in central Greece. The virtual floor is yours, Michael.
Okay, hello everybody. I hope you can see my screen.
Yes, we can see it.
Okay, so I will present you the work done in the Sperchioz River in the framework of, in the context of Operandum project. OEL Greece stands for Open Air Laboratory Greece. Open Air Laboratory is the evolution of the Living Labs term applied for open spaces and rural areas. So what we're called to do in the project and in the area of Sperchioz was to co-develop NBS solutions against flood and water scarcity, which are the most prominent hazards in the area. So to give you an overview of the location of the OEL is located in central Greece, and we have it embraces the basin, the river basin of Sperchioz River, and it covers an area of approximately 1,700 square kilometers. And as I said before, the main hydrometeorological risks relevant to our OEL are fluvial flooding because of the river and seasonal water scarcity, mainly because of the irrigation demands of the area. So in order to co-design our NBSs in OEL Greece, we had to consider several parameters. The most important one was that we needed a solution that would be effective and address both risks simultaneously. So we need to optimize the engineering and work and the funding in order to address both risks at the same time. So we needed to consider water retention measures, which will fill with water during flood events. And this water in the reservoir could be used during the periods of water scarcity. That was the main idea. To do that, we could consider the creation of sequential small ponds inside the riverbed by expanding the riverbed itself and increasing the depth of the river. The other option was to reuse the Sperchioz old riverbed, which was bypassed as a result of previous flood mitigation measures. And in fact, up to a certain length, the river has a dual riverbed. One is a man-made channel, and the other is the physical riverbed. So the most critical parameters were the ideal location, where to build the ABS, the type and efficacy of the solution, which NBS to be implemented, and time-related issues when we could implement the actual intervention. To do that, we did an extensive consultation with the local community and local experts and all the stakeholders involved in the area. So that was important for our. That was an important step in our co-design process to get in touch with everybody involved in the area one way or another, and to find out what the views were and what actually we're thinking, even if those were not real experts, but just the local community. We wanted to have their views as well. So we shared with them maps of the river basin and asked them to provide us with their expertise on the flooding events, on the water scarcity needs, and how to address that. So we got their views on those two issues. We did a lot of field trips, of course, to see on our own the area and which were the most appropriate locations, and we performed a number of measurements. Okay, now in this picture you see a very traditional type of measurement, but of course there were more complicated type of measurements. And what was actually involved in reaching the final decision was a multi-criteria decision analysis, which helped us to compare the different combination of measures and multiple important factors in our decision. So we ended up in creating a water reservoir inside the riverbed. In fact, we did two of them, one upstream and one downstream, as I will show you in the next slides. So, and here's the two interventions that we designed and built. The smaller one is upstream in a village called Zelefton, which is this intervention here. And here you see a picture of the construction phase. And the bigger one was near a village called Koma, and you see a picture of that as well here. It's nearly the before the completion. This picture taken just before we completed the work. So to achieve that, to achieve the construction phase after the let's say the consultation with the stakeholders and the selection of the proper NBS and everything, we had to go into a detailed engineering design of the actual work to be constructed, and which involved, of course, the engineering drawings and the and detailed models of the elevation in the area of the previous, considering previous flooding, considering the land use and everything. So in that picture, in the first two pictures, you see the actual engineering drawing of the intervention, and here you see a Google map photograph of the area after the construction phase was completed, and this is the retention area constructed. And here also you see the smaller one, the upstream NBS constructed in Zelefton. Here you see again the water retention area constructed in the area. Of course, to do that, as I said, we did a very thorough analysis, first of all, of the hydrological model of the whole river. You see here a run of the simulation system, which is, of course, simplified just for the use of this presentation. So we knew exactly what to expect, and we did a very thorough analysis of the hydraulic behavior of the two NBSs. Here you see the model that shows the flooding occurring in the second NBS, the larger NBS, and this allowed us to design give the NBS the proper hydraulic parameters and design the NBS with a view in the future, with an eye in the future, having the climatic change models introduced as well in the hydraulic and hydrological model, so that to design something that will withstand time and the evolving climatic changes. And okay, and having said that, I would like to thank you all, and as the rest of the team, I will be available for any questions. Thank you.
Thank you very much, Michael, for your presentation. Also to you, Mario and Kimberly. Really interesting projects, and it would be great to see these kind of examples on most of the rivers that have been channelized, right, or that are of a poor ecological status. So thank you very much for this. Now we have time for questions. So please, if you have questions, use the chat function that you can see on the bottom part of the Zoom window. So you can ask questions there. We have some questions already. So I think the first question for Mario, if I can ask you a question. The question is about the reduction in flooding using your measures. Is there any analysis or any measures that you have done to see how much you could reduce flooding, using your measures in that section of the river? Or, I mean, maybe it's not that easy, right? But is there anything like that?
Yeah. No, we of course we tried to quantify the reduction of flooding, but over the period that we had, we started in 2008 with the project, and we had of course time series before, but the flood reduction is not very big because the stretch that was revitalized is not so large, and then of course also the signal is then also modified because there are many other restoration measures along the Tor River. So you cannot really say it's because of this restoration or that. You have to look at the entire catchment. But in this case, in our case, it is more the ecological status that was improved, and recreation and so on, of course.
Yeah, thank you very much. Yeah, I think that's clear. Andrew, do you have any questions?
Yeah, there's one for Kimberly. So in general, it's often claimed that the potential of nature-based solutions to provide the intended benefits or co-benefits have not been rigorously assessed, although all three projects today showed compelling evidence for intended or achieved co-benefits. And there are also often concerns over the reliability and cost-effectiveness of nature-based solutions compared to engineering alternatives or gray infrastructure, as you noted in your presentation. So Kimberly, can you take us back to Burnaby in British Columbia? And I'm wondering if you can speak about that communications efforts with stakeholders of the classic gray versus green infrastructure debate and communicating those differences and co-benefits.
Kimberly, I think you're muted.
Can you hear me now?
Yeah, that's perfect.
Okay, all right. So yeah, no, first of all, I think Burnaby is still pretty much a beginner in green infrastructure. We have a number of pilot projects in terms of like rain gardens and permeable pavements within throughout the city, but again, yeah, that I don't think there's enough evidence out there in terms of monitoring to truly measure the co-benefits, but we know that it's there. Along the West Coast, we also have other cities like the city of Portland, whose philosophy is, to do something is better than doing nothing. So we look at, I think through our discussions, we look at nature-based solutions as not really a replacement for conveyance or for great infrastructure, but they need to work together. And that's basically where we are right now. And until we have concrete data, we will still follow through with this approach.
Thank you. Maybe I can extend that question to Mario, Professor Schirmer, if you can speak on the blended approach of course, nature-based solutions, green infrastructure, green stormwater infrastructure combined with gray, and I guess over this time horizon that that this very comprehensive project that you presented on involved, if based on evidence that you received in real time from all the different types of evaluations that were done, if there were revisions to the approach or a balancing, I guess, of additional measures of maybe additional gray infrastructure to support some the green infrastructure projects, if that makes sense.
Right. So this one example I showed, it was really quite a lot of material I had to get across. The river was cutting at one point in 2003, and then later on 7, it was cutting quite a lot into this direction of this floodplain forest, and then they had to put some arming in again. So they put some boulders in, and this then pushed back the river. So if they would have left it, probably most of the forest would have been gone. So this intervention was necessary. So this tells us, so as soon as we do something to nature, nature always fights back. And so we still have to watch out. But I think the one more very important thing is, and I couldn't really get into that at all in any detail, there are with such solutions, there are always these co-benefits that come across. And it was really just a channelized river. And then now with all these options of people that could go for recreation there, there are many more people around. They go swimming, which wasn't done before. There was this bird population that needs gravel bars. It was gone for 100 years, and now this bird is back with all these several couples breeding there. The beaver came back and things like that. So all these things together, I think, really tell us it is a way to go. We should do these kind of things, and should really try to get nature involved again into this whole ball game, and not only just having gray infrastructure, which is also needed. You know, I'm a scientist or engineer enough to know that in some circumstances you have to balance both sides.
Thank you, Mario. There's a question for Michael from Chiara. She's asking if any digital tool have been used to support the collaborative design process during the consultations, and if you have used a multi-criteria decision analysis tool during the public meetings. Michael, you're muted. Sorry.
Yeah, sorry. No, we didn't use any digital tools for the stakeholders engagement process. We used traditional methodologies, and the tools we used were mainly questionnaires, surveys, the whiteboard, brainstorming process, and things like this. No, not a specific digital tool.
Thank you very much. There's another question for you, Michael, regarding the similar measures in other rivers in Greece. If you are aware of any other rivers where this kind of retention basins have been constructed.
No, I don't know. Not as a nature-based solution. So water retention measures have been constructed in other rivers, but not as nature-based solutions to my knowledge. But I cannot be certain about that.
Mm-hmm. Great. And there's a kind of addition to that question: if there will be any kind of other measures taken to mitigate flooding, such as reforestation, perhaps along the river, or similar measures that could be quite cost efficient.
Yeah. Well, in the specific area, and that it's a bit answering the other questions to my colleagues. We didn't have an option. It's a Natura area, so the only solution that we could go for was the nature-based solution. And reforestation is not an option as well, because the area of intervention is mainly agricultural area, is privately owned land, so we cannot really take any such measures at this particular area. The upstream area of the river, of course, is a forested area. There's there, but we don't have any flooding events in the sense that we have in the downstream area, where we have large irrigation, large agricultural and farming areas. So no forest reforestation in the area. What we're planning to do, however, is to provide our NBSs with recreational value and provide the local community with some sort of small parks around the NBS interventions. And this is planning and working on right.
Great, very interesting idea. Yeah, indeed. Yeah, I think we don't have any more questions. Andrew, do you see any other questions? I think it would.
There was one in the private chat for Kimberly. If maybe you can go a little bit deeper on the dike standards and the revision of the standards, and of course the intended transferability of them just to other jurisdictions and contexts.
So we're still working on that. We did manage to bring the inspector of dikes into our discussions, and locally, the inspector of dikes basically depend on the local engineer to be able to justify, the effects of what you build. And then provide the required dike elevations. So we're going to work on that. But now that we have some support from Daltares, we will continue to maybe engage local engineers and bring them on board and see if we can come up with a final study that can incorporate all of these options together and be able to reduce our required dike elevations along the creek. We're not going to be able to eliminate dikes along the creek, but at least we can have dikes with lesser footprints.
Thank you. And just to sort of wrap up that sentiment, I wanted to emphasize, I guess, the importance of your engagement with the local engineers, and presumably likewise with Michael and Mario's dual hats that they wear in universities and education, continuing education, and the curricula for engineers of sharing these types of lessons and the driving home the importance of nature-based solutions in engineering education, and likewise in Kimberly Wong's example with the existing workforce of engineers in practice. Thank you. Yuri, if you want to wrap it up, please.
Yeah, no, thank you for mentioning this, Andrew. Yeah, indeed, this is great that this is happening. Nature-based solutions are becoming more obvious options, but also pushed by people like Mario, Michael, and Kimberly, and this is really great. I think we have no other questions, so I would like to close the webinar. And apologies for my camera; it's not working. It's maybe too many meetings, as you know, during Corona, so maybe because of that. So thank you very much for your participation. Thank you to the speakers for your great inputs for this webinar. It was very interesting, and I hope that the attendees and we will be able to use these lessons learned in our work in the future. And if you have any other questions, you can also drop us an email, or you can get in touch with us. You can go to our website. There is a email you can use And you can get in touch with us if you're interested to understand better the project or to get in touch with the speakers. So yeah, thank you very much on behalf of the project, and have a nice Christmas, and hope to see you in other events next year. So thank you. Bye-bye.
Very much. Bye-bye.